In this tutorial we're going to look at calculating a bending moment diagram and shear force diagram on a simply supported beam. So the example we've got here is a 5 meter long simply supported beam with a 3 meter long 4 kilonewton per meter line load, starting on the left going towards the right hand side. If you're not familiar on how to identify a simply supported beam, just a quick rule of thumb is you identify the number of reactions. So we have a vertical reaction on this pinned support, we also have a horizontal reaction, and we have one vertical reaction here, and we'll call this side A, and we'll call this side B, and this will be AY, this will be BY, and this can be AX. And that's a total of 3 number of reactions for one member, so that means this beam's in equilibrium. So the first thing we want to do is find our reactions. So that's our first step, reactions. The second step, we take our reactions and find our shear forces. And then our third step is to find our bending moments. And it's these 2 steps which you're probably most interested in, but this step is necessary. So we're going to set up our grid. So we're going to say everything that's vertically up and across is positive, and any moments which are clockwise are also positive, and this will keep us on track. So the first thing we want to do is take the sum of our forces. So if we take the sum of forces in the horizontal axis, so we know that's equal to 0 because the beam's in equilibrium. We have no forces in this axis, so we know that AX therefore equals 0. If we take our sum of forces in our vertical axis, in the y-axis, we know this is also equal to 0. So we know that we're going to have AY, because that is in the positive axis, plus BY, because that is also resisting upwards. And we've then got forces which are pushing down. So the total sum of these forces is 4 kilonewtons over the 3 meters, so that's 12 kilonewtons. I'll make this squiggly so we know that it's just the sum of them forces. So that's going to be equal to minus 12 kilonewtons, and that will all equal out to be 0. Now to find A and B, we don't know what they are at the moment. There's a simple method to calculate these. So we know both our supports, we're going to have a moment of 0 because they are both pinned. So if we take the sum of forces at support A, so MA equals 0, we can then find out what BY is. So if we work left to right, we know we've got this total 12 kilonewton force, which is acting here, and that's acting 1.5 meters away from the support. So we're going to have 12 kilonewtons times 1.5 meters. I'll put these in brackets. And that's going to be acting positively. So imagine we had, imagine our support A is a hinge, and that beam's just sticking out, and we've actually got our 12 kilonewton force pushing our hinge around, kind of like a swing ball. That's a very poor arrow. So that's going around in our clockwise direction, so it's going to be positive. If we move further along the beam, we've got no load, but then when we get to reaction B, we've got reaction BY a bit further along, pushing the beam back round again in the anti-clockwise direction, so that's going to be negative. So we've got BY, and that's acting a total of 5 meters away, so the lever arm's 5 meters. 5 meters. And then all of that equals out to 0, as we said before. If we rearrange this equation, we can actually find out what BY is. So BY should equal to 12 times 5, which is 18 kilonewton meters, divided by the 5 from the BY meters, and that should give us something like, let me just put that in my calculator, 3.6 kilonewtons. Okay, so we've now found By, and we can sub that back into this equation up here, equation 1, and that should give us Ay equals 12 kilonewtons, which is the sum of our total forces. Take away 3.6 kilonewtons, and that should give us 8.4 kilonewtons. Okay, so that looks about right. So we've got our beam, we've got 8.5 kilonewtons at the end. It's more heavily loaded, so that makes more sense. Let's draw that back out quickly. Something like that's so weak. Meter. We've got A direction. Let's go that up. We've got 8.4 here. We've got 3.6 here. This is equal to 0. Put in our lengths. This is not to scale, I apologise. Let's get this. 3 meters, 2 meters. Okay, so this is now a complete beam. So we found our reactions, and the next step is to calculate our shear forces. So I like to set up a grid, and a lot of people do. This is quite popular. So you set vertical lines at points of interest. So that'll be a support. So we set one up here, and we'll set up one here. And other points of interest is where we have either point loads, moments, or where a line load ends on a beam. So line load ends 3 meters along. So here, so we've got 3 points of interest. We'll draw a line across. Okay, and yeah, so we'll start here. And this is axis. This is a positive axis, and this is the negative axis, and this is going to be 0 shear force. So it's a shear force diagram, and everything's in kilonewtons. Okay, so I like to work from left and go right, and that's pretty standard. So starting at reaction, we've got an 8.4 kilonewton force, well, reaction, pushing us up. So that will actually push us up and take us to about here. And this jump is going to be 8.4. So here, we've got 8.4. So we're up here, and we now have to jump from this point to a second point of interest, which is here. And in between them points, we've got this line load, poorly drawn up here, and that is forcing us down. As we said before, that's forcing us down a total of 4 kilonewtons per meter over 3 meters, which is going to be a total of 12 kilonewtons. So we know between here and here, we're going to have negative 12 kilonewtons pushing us down. That's going to take us down, negative 12, and that will bring us down to negative 3.6 kilonewtons. And that line's going to be linear because as we go along, we've got a line load, and that's slowly pushing us down incrementally as we go down. So we can expect our line to be a nice linear line, something like this. Now we've got to go from our second point to our third point here. Nothing's happening in between here and there because there's no forces, so we can expect the line to be straight. But when we get to right hand side connection B, we've got the reaction force of 3.6, which is pushing us back up. So this is actually making us jump up, plus 3.6, and that takes us up to here, and that brings us back to 0. So that's typically what our shear force diagram is going to look like. One thing that we need to note is this point here. So next thing we're going to do is do our bending moment diagram, but because we have a shear force diagram crossing the 0 axis, this is a point of interest where our bending moment diagram is going to have a peak in it, and it's going to be our point of maximum bending moment. So we actually need to find the distance between here and here, which is going to be, we'll call it x for now. We know we can easily calculate x because we know that this jump from here to here is 8.4, and we know it's reducing at a rate of 4 kilonewtons per meter, so we can rearrange that equation. So what would that be? X equals, and that's 8.4 divided by 4 kilonewtons per meter, and that should be kilonewtons in there, but I forgot to write that, and that will is 2.1 meters. So our point of interest is acting 2.1 meters along the beam. Okay, so now on to our bending moment diagram. This can now be achieved because we've first calculated the reactions in our beam, and we found the shear forces, and now we can calculate the bending moment diagram, the final step in the procedure. So as before, we've got we're going to work from left to right, and this is going to be our bending moment diagram, and that's in everything's in kilonewton meters. I set up the same grid again as before, but this time we've got 4 points of interest. So we've got our reactions at both ends. We've got the same point of interest here where our line load ends, and we've equated an extra one from this point here in our shear force diagram where the shear force goes to 0, which is a point of interest in our bending moment diagram, because we know that's where we're going to have a peak in bending moment. So this is point 1, this can be point 2, this can be point 3, and this is point 4. So starting at point 1, we know our bending moment is going to be 0, and we'll call this a positive factor, negative, because we've got a pin support and our bending moment is going to be 0. Looking at our shear force diagram, we've got a positive shear force, so we know our bending moment is going to be increasing from that. And because we've got a linear line on our shear force, we're going to have a parabolic line in bending moment. So the change from this point to point 2 is going to increase. And because at point 2 we know we're going to have a peak because of our 0 shear force, we can expect our line to be like this. So to find the value at point 2, we're going to work from left to right, and we're going to make a cut at point 2. So let's go to here. So let's call this moment at 2. So let's say our cut at point 2 is made here, and this is actually a pin. Here's our beam, and we've got our reaction pointing up, which is reaction AY, which was 8.4. But we've also on the beam, we've got our 4 kilonewton line load per meter. This is point 2, which is, as we calculated before when we were finding x, is 2.1 meters along our beam. 1 meters. So moment 2 is going to look something like 8.4 times 2.1, which is the lever arm, from here to here. Take away 4 kilonewtons per meter times our 2.1 to get the total load, and then the lever arm of that, we know line loads act at halfway along, so 2.1 divided by 2, which is 1.05 meters, and that gives us, let me just put that in a calculator, 8.4 times 2.1, take away 4 times 2.1 times 1.05, that gives 8.82 kilonewton meters. So up here is going to be 8.82. So on to our next point, which will be moment point 3 here. We're going to have a decrease in our moment, and we know that because our shear force is in the negative axis. So we know our line is going to look something. We'll just add this line. So that's a poor parabolic line. I'm sorry. It's going to go down. And to find the distance it's going to go down to, we need to find the moment at point point 3, we are going to do the same as we've done before. We're going to assume we made a cut at point 3 and we're looking at everything from the left-hand side of that cut. So draw a line along here, and here's our point 3, and assume it's a hinge again. So we're going to have our 8.4 reaction. We're going to have our 4 kilonewton per meter line load. Space, I'll put that there. This is kilonewtons, and that is acting across a distance of 3 meters. So if we want to take the value of M3, we're going to have 8.4 kilonewtons times 3 meters, and that's our lever arm. Take away 4 kilonewtons per meter times by 3 meters to get the total load, times by the lever arm, which is here, because we know total force in our line load acts halfway between. Centroid is 1.5 meters. And if we punch all that into our calculator, times 3, take away 4, times 3 times 1.5, means the moment at that location, point 3, is 7.2 kilonewton meters. So that's 8.2, it's actually somewhere about here, 7.2. It's going to go down to that point. That is a very poorly drawn line. It would be a lot smoother if it was computer generated. So we now need to go from point 3 to 4. I'm running out of room, so okay, so point 3 to 4. We can expect our line to be also decreasing, because if we go back up to our shear force diagram, our shear force is in the negative axis. And because this line is a flat line, line down here is actually going to be linear this time. So it's going to be a straight line. And if we have actually calculated everything correctly, our moment back at our support should theoretically be 0, because we've got a pin support. But we're going to calculate it anyway. So if we come down to here, and let's say M4, and we take a cut just to the left hand side, like a tiny amount to the left hand side of point 4, just to the left hand side of our support, and that's point 4, and we look at everything that's happened on the left hand side. We've got 8.4 kilonewtons pushing us up, and then we've got 4 kilonewton per meter line load acting up to 3 meters along the beam. And if we draw this out, some lengths, it's a fairly straight line. Well done. So that's 3 meters, that's 2 meters, and we want to equate this out. So let's go M4. That's going to be 8.4 kilonewtons, and this time we've got a 5 meter lever arm back to our point 4, so times 5, and then that's going to be take away. So we've got our 4 kilonewton line load, and that's actually across a whole 3 meters this time, so we know that's going to be 12. So 4 times 3 meters. And our lever arm is, we know it's acting at halfway point here, so that's going to be 1.5 meters to there, plus another 2, so 3.5 meters. That's going to equal out to hopefully 0. And if it does equal 0, we know we are correct. Yep, 0. So 0 kilonewton meters. So we're back to our point 0 here. So this is it. We've got our shear force diagram and our bending moment diagram. And that is how you calculate it. So I'm sorry about the messy video. I'm still getting used to a pen here. Hopefully I'm going to have some more examples uploaded to the channel later on, so you can just click through them. Hopefully I'll have a different variety of different level difficulties, so if you're prepping for an exam you should be pretty well covered. Um, yeah, thanks for watching the video. Subscribe and also give it a like if you enjoyed it. And if you spotted any mistakes or have any questions, just leave a comment in the comment section and let me know.